What are the ortho-para and meta directors? In a benzene ring like this, these two positions are called ortho positions. These two positions are called meta positions. And this position that is very far from the number one carbon position is called the para position. Here, S signifies the substituent on the benzene ring. Now, ortho-para and meta directors. The substituent on the benzene ring determines where the electrophile enters during electrophilic substitution. When an electrophilic attack occurs on benzene ring, the substituent that is already on the ring determines whether this species will be at the ortho or para position or at the meta position. So, what are the ortho-para and meta directors? These are substituents on the benzene ring that directs the incoming substituents to the ortho-para position or the meta position. Ortho and para positions or the meta position. These are the two probable positions that an incoming species will enter. So before we go further to determine which groups here are ortho-para or meta directors, the substituent, the group on the benzene ring is classified into two. Activating / deactivating. Activating / deactivating groups. Then ortho-para / meta directors. Activating groups, what they do is to activate the benzene ring by pushing electrons, pumping electron clouds into the benzene ring, making benzene ring more susceptible to electrophilic attack. That is, the incoming substituent wants more electrons. So, what the activating group does is to push more electron cloud to benzene and making benzene more susceptible for the reaction. Why the activating groups? What they do is to abstract electron cloud from benzene and make this less susceptible, less electron rich. Let me just use the term, less electron rich for the reaction. These are the activating groups. You can see they are electron cloud pushing groups. They push electron cloud to increase the electron cloud of the benzene ring. You see that the atom directly linked to benzene are responsible for pushing the electron cloud into the benzene ring. These are amine, methyl group, hydroxy group, methoxy group, amide group. Deactivating groups they decrease the electron cloud of the benzene. These are the examples of the group. You see, this nitrogen is the one directly linked to benzene, but it has a highly electronegative oxygen which withdraws the electrons from it, which in turn makes sure that the electron cloud in benzene decreases. The same thing like as this. The carbon here has oxygen attached to it, which is electron withdrawing. Also this sulfur has oxygen nebel. You know, halogens are naturally electron withdrawing. So these are the activating groups. So experiment shows that all the activating groups are ortho-para directors. And all the deactivating groups except the halogen groups are meta directors. What do we mean by ortho-para directors? These groups direct the incoming substituent to either ortho or para position. Why these ones, except these are also ortho-para directors. So these ones now are meta directors. Let's take OH group as ortho-para director. Now, how do we know that a particular substituent is ortho-para director or even meta director? It is by drawing the canonical structures of the products formed by introducing a particular substituent. The higher the number of canonical structure, the more stabilizing, energetically stabilizing the product would be. So the one we have, if we intentionally direct an incoming substituent to ortho position or para position, and we get a more number of canonical structure than when we direct it to meta position, we now know that this substituent is ortho-para director, because what the canonical structure shows is the extent that the positive charge created in the molecule has gone. You know, the highly distributed the positive charge is determines the product that is energetically stabilizing and the product that is energetically less stabilizing. Let us take phenol, for instance. Phenol has OH. So let's try to nitrate phenol. So in nitrating phenol, nitrosonium ion, which is positively charged, is added to the ortho position or para position, so that we see how the extent of distributing this positive charge around the structure. So we begin. This bond we first break into this positive center, because this is a pi bond. The electron moves into positive center, and we now have a canonical structure. This is a canonical structure. This bond does not exist again, but this is there. This one is there. Then we have our NO with H. There is H here, there is H in all these places, but let me deliberately show this H. Now, you see that this is where the bond was broken from. This particular carbon will now bear a positive charge. Because of that, the pi electron here will move into this place and re-establish itself in order to annul this positive charge. This alone will create another canonical structure. It will create this canonical structure where we now have new bond here, and the positive charge will now re-establish itself here. Because of this, the pi electron here, they will move into this place to annul this positive charge, and we are going to create another canonical structure. So new bond will form here, and this one will disappear, meaning that this carbon will become positive. If that is so, the lone pair in oxygen here we move down here to establish double bond between oxygen and carbon, and we form another canonical structure. Double bond oxygen hydrogen. Now the oxygen will carry a positive charge, and if you check, you see that there is no going further again. The number of canonical structures are 1, 2, 3, 4. You see the extent the positive charge is distributed from here to here, from here to here, from here finally to oxygen. Okay, theoretically, this is what we have gotten by deliberately positioning NO to the ortho position. Let us now position NO to meta position and see how many canonical structures we will get. So we have our phenol. This is our phenol. we now put our NO plus. This bond moves into this place, and NO is positioned at the meta position this time around. Meta. NO at the meta position, which means that the positive, look at double bond here and here, this one has disappeared. The positive center is going to be here at this carbon. When that is so, it means we are going to, this pi electron is going to move in here. Remember, if you try to move in the lone pair of oxygen here, you will create 4 bonds around carbon, which is not possible. So we move in this pi electron into this place to create another canonical structure. It's now here. The positive charge has disappeared. It is now re-established here. And you know that there is a pi electron. There are pi electrons here. They will also move in here to establish another bond. And we have another canonical structure. So because the bond here has disappeared, we have positive charge here. Remember, our NO is still here. Our NO is still here. If you look at this structure very well, you see that there is no way you can move the pi electron again. If you return it here, you create this one again. You see, if you keep returning, you get the previous one, the first one. And you can't bring this pair of electron here. You create 4 bonds. So you can see there are 3 canonical structures, A, B, C, which is less energetically stabilizing or more energetically destabilizing. The distribution of electron here is among only 3 points, 3 carbons, 1, 2, and 3. But here the distribution is far that we have the positive charge here, we have here, you know, we have here, and we also have on oxygen. So the extent of positive charge distribution is far, creating more canonical structure. Therefore, OH group is an ortho-para, ortho-para director. That when you have this kind of reaction, practically, you will see more percentage of this compound. I mean, this canonical structure can be resolved to be something like this. It can be resolved to be something like this. You know, it can be something like this. You will have more percentage of this. This is ortho compound. Or you can get something like this, where NO is at the para position. You see, you will get more percentage of this kind of compound, but extremely lower percentage of this kind of compound. Extremely lower percentage of this, showing that reactions tend towards the product that is less energetically destabilizing. I mean, reactions tend towards the products that are more stable than products that are less stable. I hope you got value. If you did, please share this video, comment, and follow my Facebook channels and TikTok account. And finally, subscribe to my YouTube channel, Anselm Igwe Educational Consultancy.